Now, when motion is curvilinear in multiple dimensions, then the particle is not following a straight path. So you need to pick what type of coordinate frame to use. There are different types of frames. So your different options for coordinate frames. So the first one is Cartesian. This is that normal XYZ. And we use Cartesian when the frame can be static. So Cartesian frame does not move. X, Y, Z. So the particle can be doing whatever it wants. The frame is just there and you track that particle as it's going around. This is generally easiest to use when the path is straight. So maybe it's not just along the x-axis. It's like that or something, but it's generally easiest to use for a straight path or if you know the path. Then the second option is polar. Also known as cylindrical. So the polar is r theta, and then the cylindrical part, if it's 3 dimensions, so this is 2D, this is 3D, r theta z. So for this, r always points towards the particle. So this is the r vector. We use u because it's a unit vector. So ur, u theta, and then uz, which is really just k hat. These are also, x is notated as I hat, y is j hat, z is k hat. So in this polar system, the ur vector always points towards the particle. So that means if the particle is moving on this path, ur is pointing right there. Now, if the particle moves, so let's say it moves to here, now this is going to rotate. Okay, so ur always points towards the particle since that has rotated. Now, because this frame is not static, polar rotates with the particle. The z vector is constant, but the ur and the u theta are going to rotate. The Cartesian one is static. That frame doesn't move no matter what. And then the last type is normal tangential. This type of coordinate frame is basically the last resort. It's attached to the particle. So say your particle is moving in a path like that. If your particle is here, then the normal vector points into the center of the curve, un. And then the tangential vector points along the path, ut, but it's attached to the particle. So then let's say your particle is over here now. Then the un points into the center. Ut points along the path. So if you look at this, it can be confusing because on here, ut is pointing to the right and un is pointing to the left. Down here, UN is pointing to the right and UT is pointing to the left. So the direction of UN relative to UT flips based on whether the particle is sort of going in like it's on the concavity of its path. Also, because it is attached to the particle, then the position of the particle is always at the origin of the system. So its R vector is always 0. So normal tangential can be really difficult to actually like extract information about your system from. So this is a last resort. In most situations, Cartesian, polar, that's what you want to stick with. So we'll actually look at when do you use each type of system. So which coordinate frame you use depends on the motion that your particle is going in. So to start, the first thing you do, start here, is you want to check the path. Check the shape of the path. If it is straight, then we go with Cartesian. So you want to use that static frame if the particle moves in straight lines. Then if it is not straight, so say it is curved, then the next thing you have to do is check to see if R, or the path, is known or unknown. Do we know the position vector, the R? If we do know the path, or if we don't know the path, those will give us different answers. So if we don't know the path, use polar. If you do know the path, then check to see if R is a function of theta. If it is a function of theta, use polar. So here you see the R, theta, z. If theta is in there, R is a function of theta, then we use polar. If it is not, then we use normal tangential. So this is last resort. So straight, use Cartesian. Curved, see if you know the path. If you don't know the path, go with polar. If you do, see if R is a function of theta. If it is a function of theta, go with polar. If you've exhausted everything else, go with normal tangential.